Hi there, students. Just wanted to prepare you for the upcoming quiz on 6.1 and 6.2. Whenever that's going to be, we'll announce it during class and talk about it. Here are 3 things you should know about exponential functions and compound interest and growth and decay, not necessarily in that order. So, first things first, just the basics of exponential functions. You should remember that all exponential functions have the basic form of y equals a times b to the x, where a will always represent the y-intercept, and b will tell us whether it's growth or decay. And then under what circumstances will that happen? It will be growth if b is greater than 1, and decay if the value of b is between 0 and 1. And understand that a negative x in the exponent will basically switch those ideas. So, 2 to the x is growth, but 2 to the minus x is the same as 1 over 2 to the x, which is now decay. The domain for all exponential functions is unlimited. It is from negative infinity to infinity. Some people say all real numbers, or the symbol for all real numbers. And the range for these is from 0 to infinity, which means there is a horizontal asymptote at y equals 0. And the end behavior for these functions as x gets large, we're assuming for growth right now, as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, the function heads towards 0. We would flip-flop those if it were decay rather, so you can see growth has the infinite behavior as x goes to infinity, and 0 behavior as it goes to negative infinity. But for decay, the opposite happens. As x goes to infinity, the function heads towards 0. And as x goes to negative infinity, the function goes up to infinity. Okay, so a quick recap on basics of exponentials. Do these things change when we start transforming the function, moving it up or down, flipping it, stretching it? Yes, but this is just meant to be an introductory topic for basic exponential functions of the form y equals a times b to the x. Now, growth versus decay, we're going to get a little bit more involved here, where r is essentially the rate of growth or decay. Maybe you have an investment that is growing at the rate of 8% per year, like a bond. That's a guaranteed 8% per year. Maybe you have a car that for insurance purposes is depreciating in value at a rate of 12% per year. Or machinery in an office for tax purposes can be considered to be depreciating at a consistent percentage per year. So these lead to growth or decay situations, and we can simply modify our formula y equals a times b to the x. We're just going to modify the base. When it's growth, the initial amount is still the same, but now it's 1 plus r. And I'm going to change the variable to t because t represents time. Similarly, if we're in a decay situation, it's going to be 1 minus r to the t, basically representing the amount of the value that is left. So if I'm growing at 10% per year, I'm adding 10% of value. If I'm depreciating at 10% per year, I'm losing 10% of value per year. So it gets subtracted away from or added to the 100%, the full amount that exists in that previous year. Moving down to the last topic here, compound interest, as you can see, is basically a slight revamping of the growth formula because compound interest will speak about growth. So if we compare it to the original formula, a equals 1 plus r to the t, you'll notice the only new piece of information is this n, where n represents the number of times per year that the interest is compounded. So we're going to call this a finite situation. Maybe it's maybe it's 4 times per year, which we would call quarterly, or maybe it's 12 times per year, which would be monthly, and so on. Any finite number of compoundings would get this treatment. Daily would be 365. What did I leave out? Weekly could be 52. I suppose you could say every hour. I think there's 8,760 hours in a year, but at that point you're starting to get ridiculous. But there is an upper limit to that, like how frequently could you compound? Could we do it every second, every tenth of a second, which is going to lead us into this other piece here, this continuous compounding. But for now, just know that P, R, and T are the normal values from before. P is the principal, R is the rate of interest or growth, and T is time, usually in years. N is the number of compoundings per year. Okay, and then over to the right here, when we talk about continuous compounding, that again is the upper limit of, how frequently can you compound something? Every hour, every minute, every second, every tenth of a second, every hundredth of a second. There comes a point where you're breaking time into an infinite number of intervals. And essentially that's what the continuous formula captures. So everything is the same here. We call it the PERT formula, or at least I do. P, R, and T are what they are in the previous example, but E is now this constant, which is about 2.718. It's an irrational number like pi. They're very easy calculations to make. I think the compound interest problems are extremely easy. I think you'll find them the same way. So let's jump in to just 4 problems that I selected here. And these are just, I had ChatGPT rework some of my homework problems. And let's see if we can kind of hack into these right away. All right, so number 1, you take a 500 milligram dose of an antibiotic. And during each subsequent hour, the amount of medication in your bloodstream decreases by 18% per hour. That's a situation of decay. So in part A, we are asked to write an exponential model. So it must follow, going back to, let me go back to the previous page, it's going to follow this model here, the decay model, y equals a times 1 minus r to the t. Well, my rate of decay is 18%, and I'm always going to express it as a decimal. And there's initially 500 milligrams of the antibiotic in my bloodstream. So this is my model, and I'll just simplify it. 1 minus 0.18 is 0.82. This is my model for part A. In part B, how long would it take to decrease to 200 milligrams? Well, we don't have the tools yet to solve this, so we're going to rely on a graphing calculator or Desmos. For right now, I'm going to use Desmos because it's easier for me to model right now on my iPad. So I've already set it up. Essentially, we're trying to solve the equation 200 equals 500, 0.82 to the t. So I can take each half of the equation and kind of isolate it in Desmos. I'll make this my first equation, y1, the 500 times 0.82 to the t. And I'm going to make this y2. So let me just get that set up here. Let's see, so now I should have y equals 500 times 0.82 to the x. I have to use x on Desmos. And then y equals 200. Now we can't see anything because the graph is way zoomed out, or zoomed in, I should say. I'm just going to pinch this until there's the exponential. There's an exponential decay, as you can see. And if I follow this up to 200, you will see that I get about 4.61 in terms of how long it will take to decrease to 2 milligrams, 200 milligrams. That's 4.62 hours, excuse me. So we're going to have, let me just get this back here. A little clunky. It's my first time using this equipment here. I'm trying to experiment and see what works best. So we have then T equals about 4.62 using Desmos. You can imagine this would be a little more difficult on the TI Inspire. You'll have to zoom out until you can see the intersection of both graphs. It can be frustrating. Alternatively, you could use the solve feature and that's probably easier. Just type in the equation and hit solve. But I like the graphical approach just for the discussion it provides. As far as part C goes, write an interval that represents the domain of each function. Well, we just have, we're looking at consuming some medication, and we cannot consume that in the past. We can only examine the effects from 0, in theory, to infinity. Now, I know that's kind of silly, because we know that there'll be none of the drug left in our system after, let's say, 48 hours. But in theory, according to the mathematical model, the domain is from 0 to infinity. So take that for what it's worth. Okay, so that is the first problem. The second problem deals with the half-life. And I really like this problem because it deals with like a change in the base of the exponent. And let's talk about this for a minute. It says here the amount y in grams of a radioactive substance after t years is modeled by this function. And we have a equals 0.5. That really represents a half-life situation, raised to the t over 1600. Now what that really means is, I think we talked about this in class, is that every 1600 years the population or the amount of the radioactive substance gets cut in half. So the question behind the question here is, what percent of the substance is released in 1 year? Right? So it takes 1600 years for it to decay to half. And geometrically speaking, how much is released in 1 year? As you can imagine, it will be a very, very small amount. But let's dig under the hood and see if we can figure it out. So right now we have y, whoops, I'm going to go back to pencil. Y equals a times 0.5 to the t over 1600. Now, I want the base just to be t, so I know what it is per year. The original amount really doesn't matter to me. It could be 100 grams, a kilogram, 20 kilograms. We really want to focus on what's inside of the base here. So I want you to imagine that this base is 0.5 to the 1 over 1600. Because what happens when we have a power raised to a power, right? We have 1 over 1600, 0.5 to the 1 over 1600, which is raised to the t. When you have a power to a power, you're just multiplying. So this setup gives us the original base, and therefore it confirms for us that what's here in yellow actually is a valid representation of the base if the outside exponent is going to be raised to the t. So if I can simply simplify that and figure out what is 0.5 raised to the 1 over 1600, okay, that's going to be 0.9996. I'm going to write that down. 0.9996. So this is a 0.9996 to the t. That's the percent that remains every year, right? You can imagine it's only losing a little bit of its population every year because it takes 1600 years to be chopped in half. So the question says, what percent of the substance is released? I could simply say 1 minus, just realized I'm off the screen there, 1 minus 0.9996, and get 0.0004 or about 0.4% per year is what it's losing. All made possible because we rewrote the base. We took that, I'm going to write it again. We took that 0.5 to the t over 1600 and reimagined it as 0.5 to the 1 over 1600 times t, right? Because these numbers are being multiplied to give us t over 1600, we simply just found the numerical value of that. It was 0.9996, and that meant we were losing about 0.04% every year. Maybe conceptually a little difficult, but numerically actually very easy. Okay, so that's those two problems. And the back two problems here all deal with compound interest. It's all formulaic. I believe you'll find these to be very easy. I'm going to remind you of the formula for compound interest when it's compounded finitely. So an initial deposit of $7,500, that's my principal, is made in an account paying 3.4% interest. That's my interest rate expressed as a decimal, compounded monthly. That means 12 times per year. Part A says find the balance in the account after 18 years. So that is n is 12 and t is 18. If you'd like to know, that number is 216. So I can just plug in this quantity into my calculator. Let's do it. Let's do 7,500 times 1 plus 0.034 by 12, close parentheses, exponent 216. And I get, or we get, $13,818.91. All right, so that's it. Took me a second there to double check that and make sure that it made sense. It does. Okay, and then part B, how long will it take to triple its triple the investment? Let's go back here. All right, so I wrote down 13,818.91. Now I want to triple the investment. So I'm going to write the same equation, but I'm going to replace the amount with 22,500. That's triple the original amount. Okay, and then I have 1 plus 0.034 over 12, but I don't know how long it's going to take. Okay, so unfortunately what I have to do here is I'm going to divide both sides by 7,500. This is going to make life a little bit easier because the left side will simplify to 3. And these numbers are just a bit smaller for the purpose of calculating. So I have 0.034 over 12 to the 12t. So I'm now going to put that in my graphing calculator or solve it on the Inspire. Let me just do this here. All right, so I'm going to knock these out. I'm going to go back to the home view. I'm going to type in y equals the right side of the equation, 1 plus 0.034 over 12. I need parentheses here. To the exponent, 12x. And the other half of my equation is y equals 3. And let's see what happens. Yeah, you can see the linear function purple and the exponential growth function in green. Where do they cross? It looks like 32.4 years to triple. So t equals, let me go back to my screen here. It's about 30, takes about 32.4 years. I'm always going to cite my source here, so I'm going to tell you that Desmos gave me that answer. You might tell me TI Inspire gave you the answer, but that's how long it takes to triple. All right, and our last problem here is a continuous compounding. This one from a little bit of a different angle, so to speak. We're going to use continuous compounding. I know it's continuous because I've read it in advance and I saw the word continuous in there. So an account currently has a balance of $420,000. The account was opened 12 years ago and has earned a constant interest rate of 2.85% compounded continuously. What was the initial investment in the account? Okay, this shouldn't be so bad because I'm going to set up my PERT formula, which is what we use for continuous compounding. It currently has a balance of $420,000. I do not know the initial investment. E is my constant for continuous growth, and the rate of interest is 0.0285, and it was 12 years ago, so times 12. Now I'm going to make this problem calculator ready. I'm going to solve it for P. And I'm not even going to calculate that. I don't like to round and then reuse that answer in a future calculation. So I'm going to keep it like this. I'm going to call up my calculator and let's see what we get. 420,000 divided by E, exponent, parentheses, 0.0285 times 12. Looks like the original amount in the account was about $298,346. Excuse me, $298,346.25. All right, so P equals $298,000, $346.25, and that wraps up part A. Part B, what was the average rate of change over the 12-year time interval? We keep putting these problems in the curriculum on purpose. Average rate of change is a very helpful thing by the time you get to calculus, so we want to keep making sure that you see that formula. If I want the average rate of change on the interval from 0 to 12, it's very simply the amount of money we had after 12 years minus the amount of money we had at the beginning over the time interval, 12 minus 0. Now we've just calculated A of 12 to be, actually we know A of 12, is 420,000. That was the original, the amount we have now. The amount at time 0 was 298, 346.25, all divided by 12. I'm going to pull this up on the calculator anyway. I don't think you need to see me do this to know what I'm doing, but I'm going to put parentheses 420,000 minus 298, 346.25, all over 12. And I'm getting about the average rate of change to be about $10,137.81 per year. So, what does that tell us? Even though the money is growing exponentially over 12 years, we could estimate that over that 12-year period, on average, the slope of this line, it's growing at a rate of $10,137 per year on average. Even though we know the further along we go, the quicker it's going to grow. All right, so just a few things. Hopefully this helps you as you study for the quiz and get ready for it next week. So I wish you the best of luck. Please email me or stop in during period 9 if you have any questions, and I look forward to seeing you in school.